Alright, so section 7.7 is on something called the natural logarithm, and it's similar to the common log. And we talked about last section, the common logarithm has a base of 10. The natural logarithm, the symbol for that is ln. I think that comes from Latin, if I remember correctly. It might mean logarithmus naturalis, which would be Latin for natural logarithm. But this basically has a base of the number e, and number e is a fascinating number. It's kind of like pi. It's this number here, 2.71828, and it goes on and on forever, just like pi. And if we had more time, we'd kind of talk about where that number comes from. It's used a lot in calculus, used in finance, and continuously compounded interest and things like that. But for now, just know that that is a number kind of like pi. It's not something that people invented. It's more like something they discovered. So a couple of things we want to do. We want to talk about changing back and forth from exponent form to natural log form. And that's done the same way as what we did earlier in the chapter with regular logs. We want to learn how to condense logarithm expressions, how to solve equations. And these are done the exact same way as we've solved other equations, just with a different base. And then finally, we'll talk about how money factors into this, how to find continuously compounded interest. So you can compound interest. That means that the interest that you make is reinvested, and that can be done annually, once a year, monthly, weekly, daily, or it can be done literally every second, and that's kind of where the number e comes from. So here's basically what this means. The natural log of 4, that's another way of saying the log, not with a base of 10, with a base of e. Okay, that's what all this stuff means right here. And if you wanted to change that, you could say, you could change it the same as we've changed other ones. This base to that power equals that answer. What confuses people sometimes about this is that they see the e and they think it's a variable. E is not a variable. Okay, e is just a symbol for a number. It's kind of like pi. Pi is not a variable. Pi is this number right here. Right? It's an actual number. E is like an actual number. It's not like an actual number. It is an actual number. 2.71828 and so on. Okay, here's what the name for e is it's called natural log because it occurs quite a bit in nature, kind of like pi naturally occurs whenever you're talking about circles, a ratio of the circumference to the diameter. Okay, so here's what the function looks like. E to the x looks like this, and its inverse function is the natural log of x, just like 2 to the x and the log base 2 of x would be inverses. E to the x and the natural log of x are inverses. And then if you raise it to a negative exponent, you get this kind of downward sloping curve right there. That's the that represents, in actual word problems, it represents something called exponential growth and decay, and we'll talk more about that in the next section, 7.8. Okay, so we want to practice changing these exponent forms to logarithmic forms, to natural logarithmic forms. So this says that log base e, and we don't need to write base e because if we're writing ln, remember ln means this. It means the log with a base of e. It's just a faster way to write it. So the log base e, this number raised to this power, equals this answer right here, equals 8. So that's how you write it in log form. Okay, same thing right here. This is going to be the log, I'll write it both ways. The log base e, e raised to this power, so e raised to the 5th power, equals this answer, equals x. And another way of writing log base e is the natural log. So the natural log of x is equal to 5. Okay. Same idea if you're changing the other way, so changing from natural log form to exponent form, we can do that using the same way. So even though it's not written here, natural log has a base of e, so this base to that power equals that answer. E to the 0.7741 is equal to x, and they're saying approximately equal because that answer has been rounded. Same thing here, that has a base of e, e raised to that power equals that answer. E to the x is equal to 10. Now that's in exponent form. Alright, now we talked about changing back and forth from exponent to log. We want to talk about how to condense things into a single log. So just to recall from an earlier section, the log of two things multiply, that's the same as adding them, adding the two numbers together. And this works the same for natural log. So the natural log of a times b would be the natural log of a plus the natural log of b. That's the multiplication power. we had a division power as well, so log of a over b, that's the log of a minus the log of b, works the same way for natural logs. So the natural log of a minus the natural log of b. And then finally, if you're taking the log of something raised to a power, you can take that and slide it in front. That's the same as b times the natural log of a. Those are all the same powers we talked about before. The only difference is we're using natural logs instead of the common log. Okay, so here we're subtracting, and if we look over here, this power right here, the division property, is the one where we subtract. So we're going to take, and actually before we do that, let's take this 3 and slide it back up here as a power. That's this one right here. So this is the same as the natural log of 10 to the third minus the natural log of 8. And that's the same as the natural log of this number, 10 to the third, divided by this number. And the natural log of 10 to the third is 1,000. So 1,000 divided by 8, and that is 125. So if you put that in a calculator and you put this in a calculator, you would get the exact same number. That's a nice way to check. Okay, this one's a little bit trickier. So we have a bunch of stuff being multiplied together, and then we have numbers in front. So it's always a good idea to start by taking these numbers in front and just putting them back up as powers. So we have the natural log of 40 plus the natural log of 1/2 squared plus the natural log of x. Okay, let's put these back together. So we're adding these together, so that means we must have started out by multiplying them. So 40 times 1/2 squared times x. 1/2 squared is 1/4, so 40 times a fourth would be 10. That's the same thing as 10 times x, or just 10x, and that is the condensed version. That's called condensing a logarithm, because we started in something expanded form, we put it back together by condensing it. Okay, here's just something to note about properties with logarithms. What does this mean right here? Okay, this means raising e, and then the natural log of x, remember that's base e. So this right here, let me just kind of put that as a sidebar. This right here means what power do I have to raise e to get x? So this represents, let me write that, this represents the power you need to raise e to, power you must raise e to get x. So what does this mean? This means I'm raising e to the power that e needs to be raised to get x. This right here means the power I have to raise e to get x, and I'm raising e to that power right now. That's what this means. E raised to the power that e needs to be raised to get x. So if I'm raising e to the power that it has to be raised to get x, I'm going to get x, and that's why that thing equals x. It's a little bit hard to understand that first time you think about it, but try to think about it a little bit. Hopefully it will make more sense. What is this right here? This means the base e. So I'm raising e to some power, and it's giving me e to the x. What power do I have to raise e to get e to the x? I have to raise it to the x. So the ln of e to the x is just going to be x. Basically, these things kind of cancel each other out, just leaving you with the x. And we kind of saw something similar in an earlier section. Alright, so the last couple of things, we want to talk about how to solve equations. And the first thing we always need to do is get rid of anything around it. We can't take the logarithm until everything else has been cleared away. So I need to clear away this 5, or that minus 5. 3 plus 5 is 8. And then I can't take the logarithm until this 4 in front is disappeared. So I'm going to cancel out of that. Now and only at this point can I take the logarithm. So 8 divided by 4 is 2. You could take any log that you want to, but because we're raising e to a power, it's probably going to make the most sense if we take the natural log. Okay, and there's a reason why it's a little bit easier. So let's take the natural log of both sides. Okay, this, what does this happen right here? This is saying what power do I have to raise e to get e raised to that power? And the only thing you could raise e to that would give you e to the negative 2x is negative 2x. So essentially these things are kind of canceling each other out. Here's the important thing, that only works if you are raising e and you're taking the base e. So for example, let's do it with numbers just to show how this makes a little bit more sense. The log base 8 of 7 to the 42nd, the log base 9 of 7 to the 42nd, the log base 7 of 7 to the 42nd. There's only one of these three, let's call these a, b, and c. There's only one of these three where things are going to nicely cancel out, just like they canceled out with that e, and that's this one. Okay, because I'm taking the log base 7 of a power of 7, those will cancel, and I'll just get 42. That doesn't work here, and that doesn't work here. That's why we took the natural log, so that we can get those to cancel. So negative 2x equals the natural log of 2. Let's divide by negative 2. And then we want to put this in a calculator. I think it's going to be like negative 0.34, negative 0.35. And I want to show you where to find natural log on your calculator as well. So the natural log is actually, you can see it right there, it's right below the log key. So we want the natural log of 2, and then we will divide by negative 2. It's like negative 0.3466 basically. Usually round it to 4 decimals. Alright, so the last couple that we want to talk about are solving, these are solving log equations now, so it's like the opposite of what we just did. Equations are inequalities, and the only thing to be aware of with inequalities is that if we multiply or divide by a negative number, we have to change the direction of whatever way the sign is going. Okay, so that's important to keep in mind. So let's start with the one on the left. So again, we can't start changing from log form or from exponent form until everything outside of it has gone away, and we have that 3 there. You could put the 3, you could swing it over to raise 4x to the third power, but that doesn't really make a lot of sense. That would make it kind of a harder problem than it needs to be. So we'll have ln of 4x equals 24 divided by 3 is 8. Now we're in log form, we can change to exponent form. That's usually what these involve. If you're in exponent form, usually you change to log form. If you're in log form, you usually change to exponent form. We see what's being done to x and do the opposite. Right now x is having the log taken, so the opposite would be raising to the exponent. So that's base e, so this number to that power equals that answer. So e to the 8th equals 4x. We want to solve for x by dividing by 4. And whatever that is right there is going to equal x. So e to the 8th divided by 4. And it's a good time to show you where to find e on your calculator. E is located right above the division symbol. So I'm going to hit second, divide, and there is the number e. I'll raise it to the 8th power. And then I hit the arrow to come down from there, and then divide by 4. And whatever that is equal to x, 745.2395. Yeah, that's a pretty big number because e, you're raising it to the 8th power, it becomes large. Alright, this one right here. So the first thing that would be a good idea to do, because we're going from log to exponent form, there's a couple ways you could do this. I would start by taking this 4 and swinging it down front, because that's kind of how we started over on that side. We had it in front already. You don't have to do it that way, but there's probably the easiest way. Now let's divide by 4 right here. We don't have to flip the sign because we divided by a positive number. 4 divided by 4 is equal to 1. Now I'm going to raise this number to that power and get that answer. And the key is to keep the x minus 8 facing the same direction as that sign. So right now x minus 8 is less than, so it's still going to be less than when I change this e to the first power, and that's just the same thing as e. And then we will add 8 to both sides, and so we will get x is less than e plus 8, which is 10.7183 when you round it to 4 decimal places. Okay, last thing I want to show you is using this when it comes to making money. So the compound interest formula, you might remember it from an earlier section. The compound interest formula looks like this. It's the principal, that's the amount you invest, times 1 plus your rate over the number of times compounded to the nt. So this formula right here, that is used for regular interest. How does it become this formula? When the number of times you compound becomes very, very large, and I'll show you this right now. Let's suppose that you had a bank that compounded your money not monthly or daily, but literally every second of the day. Okay, so let's pick really simple numbers. Let's say you invest $1, and let's say your rate is 100% rate. Remember, if something is growing by 100%, like let's say you have $8, 100% of $8 is 8, and when you add those, you get 16. So if you have a 100% rate, that's like doubling your money. So let's use r equals 1 for 100%, and then let's compound that, like I said, every second of the day. So there's 60 seconds in a day times 60 seconds. There's a lot more than 60 seconds a day. We expand this out. 60 seconds in a minute, I meant to say. 60 seconds in a minute times 60 minutes in an hour times 24 hours a day times 365 days a year Okay, so that's the number of times we're compounding, and then we're going to take this, remember this n and this n are the same, we're going to take that huge number, and we'll just say we're doing this for 1 year, so the t will be equal to 1. I just want to show you what happens. So if you take this huge giant number here, and you plug it into the calculator, you're going to see where the number e comes from, because this is why it's called the natural log. It occurs in nature. So let's see if we can conveniently put that in. We don't need the 1 in front, because anything times 1 is itself, so I just need to worry about that big parentheses. So 1 plus 1 divided by this enormous number here, 60 times 60, 3600 times 24 times 365. Close that parentheses, close the other one, and then raise it to that same thing. So I'm putting this whole thing in parentheses. 60 times 60 times, this is kind of how they discovered E, I think, from what I remember. Okay, so now what is this going to equal? Well, let's find out. Okay, you might recognize that number right there. That is basically the same as E. Okay, it's slightly different. So if we made that number even bigger, like if you compounded every millisecond or every nanosecond, it would be even closer approximation to E. So that's why E is such an interesting number. It comes from nature. It basically tells us how things grow relative to their size. In this case, we're being asked about doubling money. But anyway, that's where the compound interest formula comes from. This whole thing right here, let me put it in a different color so you can see a little bit better. Okay, this P and this P are the same. Okay, this massive thing right here, when you actually calculate it out, it becomes E raised to the rate. Okay, we just said that this whole thing right here, that's the same thing as E, and then we were assuming that we had a rate of 100, so E to the first. Okay, so that's not really a proof, but it's just an indicator of where that number comes from. Alright, and then one thing before we get started, there's going to be a lot of decimals here. This piece of advice is worthwhile. Don't round until the very end. If you start rounding too early, it makes the calculations come out to be wrong. Okay, so let's calculate this. This is a money example. We want to see essentially how much money will be made. Two of these will be equations. One will be inequality. Okay, so the first one says, here's our formula, by the way. The amount is equal to the principal invested times E to the rate times time. So the first one says, assuming there are no deposits or withdrawals. This is somebody whose grandparents invested $3,000 into a savings account with that rate right there. And this is important. It's telling us compounded continuously, which means we're going to use that formula with E in it. Assuming no deposits or withdrawals, that means they didn't take any money out and they didn't put any money in. What will the balance be after 10 years? So we don't know this. This is what we're trying to find. The principal, P, we do know. They're telling us that we invested $3,000. E raised to the rate. The rate is 0.04. And they're being asked, or we're being asked about 10 years, so times 10. So that's another way of saying 3,000 times E. 10 times 0.04 is 0.4. So we want to know what this is right here. That's going to tell us how much money she has after 10 years. So they put in $3,000. It's compounded continuously. So not just every second, but not every nanosecond. It just basically never stops compounding. And unfortunately, in real life, I don't think they usually compound that often. It's more like monthly or daily. So pretty good. She got $4,475.47 after 10 years. Okay, that is the amount of money she earns at that rate right there. And 4% is not a superb rate either. So some funds have even better returns than that. Okay, so that is how much money she has after 10 years. Second question, B, how long will it take the balance to reach at least 10,000? So we're saying how long. How long means they're asking us about T. So we don't know what T is. We have to find that. So let's fill this in. And here's the other thing, at least 10,000. Okay, well that means we want the amount to be 10,000. We want that the amount of money we have to be either equal to that or potentially greater. So at least means greater than or equal to. Same amount of money we invested, 3,000. We get the same rate, 0.04. We don't know what T is though. I'm going to use a capital T so it doesn't confuse people and look like a plus sign. Okay, now we're going to solve this like we've solved the other equation. So we first divide by 3,000. We divide this by 3,000, so those zeros will cancel, so we're left with 10 over 3. Okay, we don't want to round yet. So e to the 0.04 times t. How do we get that t to come down from where it is? We would take the log, and the best log to take here would be the natural log, because e raised to what power will be e to the 0.04t? It's just going to be 0.04t. We're allowed to cancel those as long as we're taking the natural log, which we are. Okay, so let's expand this out. We'll get the natural log of 10 over 3 is less than or equal to. Again, we haven't had to change the sign because we're not multiplying or dividing by anything negative. Last step here is we divide by 0.04. Still don't have to change the sign because 0.04 is not a negative number. So we get t is greater than or equal to. That means the amount of time needed to reach 10,000 is whatever that number is right there. So let's find that. We'll take the natural log of 10 over 3, and we're going to divide that by 0.04, and it turns out to be 30.1 years, approximately, give or take. So 30 years, and that's pretty good because 30.1 years, you know, obviously if this were a retirement account, most people are not going to retire at 30 years old. So still plenty of time to have it grow bigger than that. And things start growing ever faster when you're talking about compound interest. Okay, last one. If her grandparents want her to have 10,000 after 18 years, how much would they need to invest? Okay, so this is kind of nice because, you know, 18 years would be when somebody's going off to college, so they have a specific goal in mind. They need to, you know, how much money do we have to put into the account? Okay, so let's kind of put this off here. So they want her to have $10,000. We don't know the amount invested, so we're going to leave P blank because we don't know that yet. We know that we're going to still get that same rate because they haven't told us any different, and we know that time is 18 years. Okay, so let's change this P to this numbers multiplied together would be 0.72. Okay, now we want to solve for P, so that means we need to divide by this other thing right here. Those will cancel because P is what we're looking for. So whatever this is right here, that's going to tell us the principal that we need to get $10,000 after 18 years. So let's see what that needs to be. So clear this for a sec. 10,000, and we're dividing by, just to be safe, we'll put it in parentheses. I don't think it would cause a problem, but when in doubt, it's safer to use parentheses just to make sure. And that is going to be, they need to invest $4,867 to have 10,000 by the time she reaches 18. Okay, so that's how you use the formula for compound interest, and it's pretty interesting. If you're interested in finance, this is kind of some of what goes on when you're calculating these numbers.